When we study chemical reactions, we usually think about bulk volumes, beakers of liquid mixing, or tanks of gas colliding. But surface chemistry focuses strictly on the boundary. It's the study of the physical phenomena that occur exactly where two different phases of matter meet, like the hard edge between a solid and a gas. To understand why this boundary is so reactive, we have to look at the forces holding the material together. Deep inside the bulk of a solid or a liquid, an atom is completely surrounded by identical neighbors. It is pulled equally in all directions, creating a perfectly balanced, stable force environment. This animation shows how that balance breaks down at the edge. When we look at the top layer of this atomic lattice, the surface particles lack neighbors on the side facing the empty space. Because they aren't surrounded, they possess residual, unbalanced attractive forces. These exposed atoms are essentially desperate to balance their environment. They act as an aggressive sink, constantly pulling in and holding on to external molecules that happen to strike the surface. This physical accumulation of molecules strictly at the boundary is called adsorption. These unbonded atomic forces transform the solid's edge into an active thermodynamic trap, perpetually seeking stability through interaction with the surrounding environment. We have to be precise with terminology here. This image of a chalk stick dipped in ink demonstrates the difference. The blue pigment particles are concentrated strictly on the outer edge. That is adsorption. But the clear solvent of the ink has diffused uniformly throughout the entire inner core of the chalk. That uniform penetration is absorption. In many real-world systems, a material might hold gas on its surface while simultaneously letting liquid penetrate its core. When both processes happen at the exact same time, we describe the combined effect simply as sorption. Naturally, the reverse mechanism also exists. When an adsorbed substance is stripped away or released back into the environment from the surface, it is called desorption. Controlling these mechanisms is highly useful. If we can master how molecules pin themselves to a localized surface, we can control how and when they react. When chaotic gas molecules hit a solid surface and freeze, their entropy drops to a negative value. Thermodynamics dictate that for any spontaneous process, Gibbs free energy, delta G, must decrease. To balance this mathematical paradox, the surface compensates by expelling a massive amount of heat. Adsorption is invariably an exothermic process. Every time a molecule is trapped, the surface's residual forces decrease, and that lost energy is released as heat. As the surface fills up, the amount of heat released gets smaller and smaller. Eventually, the heat being released exactly matches the entropy being lost. At that moment, delta G reaches zero, and the system hits equilibrium. The universe demands a strict trade-off. You cannot create structural order out of chaos at a surface boundary without paying for it in heat. Depending on the specific materials involved, the physical grip between the surface and the trapped molecule exists on a spectrum of strength. Physical adsorption, or physisorption, occurs via weak van der Waals forces. It requires no specific chemical pairing, is easily reversible, and releases little heat. Conversely, chemical adsorption, or chemisorption, holds gas molecules via actual ionic or covalent bonds. It is highly specific, usually irreversible, releases massive heat, and requires high activation energy. Interestingly, these two states can overlap. If you take a weakly physisorbed gas and raise the temperature, you can provide enough activation energy to force the molecules to break apart and form strong chemisorbed bonds. To calculate exactly how much gas a specific solid will absorb at a constant temperature, chemists use an empirical equation called the Freundlich adsorption isotherm, mapping the trapped mass directly against the ambient gas pressure. Recognizing the difference between a temporary physical hold and a permanent chemical bond is exactly how industrial engineers design materials to manipulate chemical reactions at scale. That manipulation of surface bonding is the entire basis of modern industrial catalysis. If a catalyst and the reacting chemicals are all mixed in the same liquid or gas phase, it is called homogeneous catalysis. But when a solid catalyst is used to manipulate liquid or gaseous reactants, it is known as heterogeneous catalysis. The modern adsorption theory explains how a solid surface physically speeds up a reaction without being consumed itself. It operates through a strict 5-step mechanism. In steps 1 and 2, free-floating reactant molecules diffuse toward the solid catalyst and chemisorb onto its surface, locking into the active sites. In step 3, Forced into close proximity, the reactants form an intermediate complex, fusing into a new chemical product. Finally, in steps 4 and 5, the new product desorbs, releasing its grip and diffusing away, leaving the active site empty. A successful catalyst requires two precise traits. It needs activity, the ability to chemisorb reactants strongly enough to hold them in place, but it also requires selectivity. The bonds must be weak enough to let the new product go once the reaction finishes, otherwise the surface becomes permanently blocked. We see this highly specialized selectivity in zeolites, honeycomb-structured aluminosilicates used to crack hydrocarbons in the petroleum industry, and in biological enzymes, which act as highly specific, complex catalysts to maintain life processes in plants and animals. Solid catalysts act as an anvil, where atomic bonds are broken and reforged with less energy, bypassing traditional activation requirements. Since adsorption is entirely dependent on the existence of a surface boundary, what happens to a physical system if we intentionally engineer it to have the maximum surface area possible? Look at the geometry of this 1 centimeter cube. It has a total surface area of 6 square centimeters. If we pulverize it into 1 trillion microscopic cubes, the internal bulk is exposed. The volume remains the same, but the surface area expands exponentially. When we reduce materials to particles with diameters between 1 and 1,000 nanometers and suspend them in a continuous medium, we create a colloid. Because colloidal particles are so incredibly small, their ratio of surface area to mass is enormous. In a colloidal system, the vast majority of the molecules sit on a boundary edge rather than deep inside a bulk solid. At this nanoscale, the physical behavior of the material is completely dominated by adsorption and unbalanced boundary forces, rather than gravity or basic mass. We manipulate these extreme surface area systems constantly. The cleansing action of ordinary soap relies on associated colloids, specifically structures known as micelles. This diagram outlines a soap molecule, a stearate ion. Its hydrophobic tail repels water, while its hydrophilic head attracts it. In water, the tails embed into grease droplets, forming a sphere called a micelle. The heads pull the grease off the surface, washing it away. We use the exact same principles of charged colloidal suspension to manage industrial pollution. By passing factory smoke through a highly charged electrical field, we force the carbon dust to mutually coagulate, precipitating out heavy toxins before hitting the atmosphere. Historically, we've utilized mutual coagulation in tanning animal hides, soaking positively charged biological networks in negatively charged tannins to permanently harden the material into leather. Whether isolating grease molecules in a kitchen sink or pumping gases through massive, high-pressure catalytic distillation towers to synthesize global chemical supplies, the core mechanism relies entirely on the physics of the boundary. The boundary between two phases is a highly charged, unstable zone that drives the critical chemical transformations of the modern world. By understanding the forces that pull molecules out of the void and physically lock them to a surface, we can strip away impurities, trigger complex reactions, and manipulate the atomic structures of our entire environment.